In this video, we're going to begin our discussion of runtime structures with the notion of procedure activations. Before we begin the discussion of activations, it's worth being explicit that we have two overall goals in code generation. One is to be correct, to generate code that actually faithfully implements the programmer's program. And the second is to be efficient, that code should make good use of resources, and in particular, we often care that it run quickly. And it's very easy to solve these problems in isolation. If all we care about is correctness, it's not a hard problem to generate code that's very simple but also very slow and correctly implements the program. If all we care about is speed and we don't care about getting the right answer, the problem is even easier. I can generate extremely fast programs that generate the wrong answer for any problem that you care to name. And so really, all the complications in code generation arise from trying to solve these two problems simultaneously. And what has grown up over time is a fairly elaborate framework for how a code generator and the corresponding runtime structures should be done to achieve both of these goals. Okay? And the first step in talking about that is to talk about activations. We're going to make two assumptions about the kinds of programming languages for which we're generating code. The first assumption is that execution is sequential. Given that we execute a statement, the next statement that will be executed is easy to predict. In fact, it's just a function of the statement that we just executed. So control is going to move from one point in a program to another in some well-defined order. The second assumption is that when a procedure is called, control will always return to the point immediately after the call. That is, if I execute a procedure F, and once F is done executing, control will always return to the statement that followed the point where F was called. And there are certainly programming languages and programming language features that violate these assumptions. So the most important class of programming languages that violate assumption one are ones that have concurrency. So in a concurrent program, just because I execute one statement, there's no easy way to predict what the next statement is that will be executed because it might be in a completely different thread. And for assumption two, advanced control constructs, things like exceptions and call CC. If you happen to know what call CC is, it's not important if you don't. These kinds of constructs that affect the flow of control in fairly dramatic ways can violate assumption two. So in particular, if you're familiar with catch and throw style exceptions in Java and C++, when we throw an exception, that exception might escape from multiple procedures before it is caught, and so there's no guarantee when you call a procedure, if that procedure can throw an exception, that control will ever return to the point immediately after the procedure call. Now we're going to keep these assumptions for the rest of the class. We may later on in future videos briefly discuss how we would accommodate some of these more advanced features. The material that we're going to cover is basic to all implementations, and even languages that have concurrency and exceptions build upon the ideas that we're going to discuss here. So first, a definition. When we invoke a procedure P, we're going to say that is an activation of the procedure P. And the lifetime of an activation of P is going to be all the steps that are involved in executing the procedure P, and including all the steps in the procedures that P calls. So it's going to be all the statements that are executed between the moment that P is called and the moment that P returns, including all the functions or procedures that P itself calls. We can define an analogous notion of the lifetime of a variable. So the lifetime of a variable x is going to be the portion of the execution in which x is defined. That means that it's all the steps of execution from the time that x is first created until the time when x is destroyed or deallocated. And just note here that lifetime is a dynamic concept. So this is something that applies to the executing program. We're talking about the time when the variable first comes into existence until the moment in time when it goes out of existence. And scope, on the other hand, is a static concept. Scope refers to that portion of the program text in which the variable is visible. Okay, so this is a very different idea from the lifetime of the variable. And again, it's very important to keep these two times, what happens at runtime and what happens at compile time, or what is associated with the static properties of the program, distinct in your mind. From the assumptions that we gave a couple of slides ago, we can make a simple observation, and that is that when a procedure P calls a procedure Q, then Q is going to return before P returns. And what that means is that the lifetimes of procedures are going to be properly nested. And furthermore, that means that we can illustrate or represent activation lifetimes as a tree. Let's illustrate activations with a simple example. So here's a little cool program, and as usual, it will begin running by executing the main method in the main class. So the first activation and the root of our activation tree for this program is the method main. And main is going to call the method G, and so G's lifetime, the set of instructions where G exists, or the period of time of the execution where G exists, is going to be properly contained within the execution of this call to main. And so we can illustrate that by making G a child of main. So this indicates the fact that G is a direct child of main, indicates that main calls G, and also that G's lifetime is properly contained within the lifetime of main. After G returns, main will call F, and so F will also be a child of main. And then F is itself going to call G again. So it's going to have another activation of G. And so G will also be a child of F. And this tree, that is actually the complete tree for this particular example, illustrates a number of things. First of all, as we've already said, it shows the containment of lifetimes. So again, for example, G's lifetime is contained within main. But it also shows some other interesting lifetime relationships. For example, the lifetime of this activation of G and the lifetime of that activation of F are completely disjoint because they're siblings in the tree. Their lifetimes do not overlap at all. And another thing to notice here is that there can be multiple occurrences of the same method in the activation tree. So every time the method is called, that is a separate activation. So in this particular activation tree, there are two activations of G. So here's a somewhat more complicated example that involves a recursive function. Let's begin here at the first call, so the call to main. And all main does is call F with the argument 3. So there is an activation of F from main. And then what does F do? Well, F asks if its argument is 0, and if it is, it calls G. Well, the initial argument is 3, so that's not going to be true on the first call to F. And otherwise, it calls F with the argument -1. So I'll just make a note over here on the side about what the argument is, because we'll need to keep track of that. So F is called with 3. Clearly, that is not 0. And so then F is going to be called again with the argument 2. That will result in F being called yet another time with the argument 1. And finally, F will be called with the argument 0, which will then result in a call to G. And so this is the activation tree for this particular program. And again, notice that there can be multiple activations of a procedure in the same run of the program. It just indicates that the same procedure can be called multiple times. And also note that a recursive procedure will result in nesting of activations of the same function within itself. So F calls itself, and so the lifetime, say, of the second call to F is properly contained within the lifetime of the first call to F. To sum up our discussion of activations, it's obvious, I think, that the activation tree depends on the runtime behavior of the program. So it depends on the runtime values, exactly which procedures are called and what the activation tree turns out to be. Now, this was not illustrated in our examples, but it should be obvious that the activation tree can be different for different inputs. And so the programs that I showed you didn't take input, and so we didn't have any, every time you run those programs, you'll get the same activation tree. But in general, if a program takes input, it will execute differently and may call different procedures in different orders. And finally, here's perhaps the first important point from an implementation point of view. Since activations are properly nested, we can use a stack to implement or to track the currently active activations. So let's see how we can use a stack to track activations. We'll use one of the examples that we looked at before. And what I'm going to do is I'm going to show the activation tree over here on the left, and I'm going to show the stack of currently executing activations on the right. So the stack is not going to keep track of the entire activation tree. It's only going to keep track of the activations that are currently running. So at each step of the program, the stack should contain all of the currently active or currently running activations. So the tree we already saw how to build, and we begin by executing main, so that will be the root of the tree. And since the stack is supposed to have all of the currently running activations, the stack will have to have main on it. So it'll begin with just the procedure main. And now main calls G, and so G becomes a child of main, and over here on the stack, we would push G onto the stack. And then G returns, and what that means is that the G is no longer running, and so G would get popped off the stack, and then the main procedure calls F, and so F would get pushed onto the stack. And you can see here that after G finishes, we can pop it off, and then we can push on F, and we maintain the invariant that we have a stack of the currently running activations. All right, and then F is going to call G. I forgot to complete my tree here, so main calls F, and then F calls G. All right, so now the stack at this point is main, F, and G. And once G finishes running, it will be popped off the stack because it's no longer executing. And then F will finish, and F will also get popped off the stack. And finally, main will finish, and main will also be popped off the stack. And so that's the idea. So that is how we can use a stack. So essentially, when a procedure is called, we'll push an activation for that procedure onto the stack. And when a procedure returns, we will pop that activation off the stack. And because activation lifetimes are properly nested, this will work out. So to conclude our discussion of activations, let's return to the runtime organization. As you may recall, we have a block of memory that is allocated to the program, and the first portion of that block is occupied by the code for the program itself. And now, in the rest of that memory that's allocated to the program, we're going to have to store the data that the program needs to execute. And one of the important structures that goes there is the stack of activations. So typically, this would start after the code area, and the stack would grow towards the other end of the memory space of the program. And the stack will grow when procedures are called, and it will shrink when procedures return. And as we'll see, there are other things that go in this data area that we are going to be discussing in the upcoming videos.